This lecture would attempt to summarize some of the common products from photogrammetry. The number one product is, of course, aerial photograph, but there are other important products out of the aerial photographs which we generate from in order to use that in other methods of data capturing. So let's look a bit more into more details of some of the different types of products. Our table of content is as shown. We're going to first look at a photo map, which is a common product from photogrammetry. Then we're going to look at mosaics, and there are different types of mosaics. There are the uncontrolled mosaics and the controlled mosaics. Another common, more popular product from photogrammetry is orthophotos, and these are photographs that aerial photographs from which the errors of tilt and relief are removed and the entire photograph is rectified and a coordinate system is defined. Another product is your DEM, digital elevation model. There are quite a few DEM available online for free, and some of these DEM were generated from photogrammetry. The photo map is a end product from photogrammetry from which the photographs are used directly. So what you would typically do is get a high resolution scanner and scan in, convert them into digital data by scanning the photographs and then merging them together to the best of your ability. And using that template of photographs, planners would typically use that to trace out where features are, and it's a rough method of capturing your data using photos in the background. Please note that these maps are typically it's usually hard copy, especially used in developing countries, and where features are traced out using markers or pencils. With you would overlay transparency or tracing paper and extract the features of interest. For main uses is for planning purposes. It is not survey grade accuracy. There are some techniques, and this is where we would try to introduce computer assisted techniques to speed up the process. So you would scan in the aerial photograph and the computer software would merge them together. This is an example of a photo map. As you can see in the background, we have buildings, and you can actually see roads and open areas, and here you can see a more highly concentrated residential building area as compared to the larger buildings. On top of that map, you can see drawn in or traced over the river, both sides of the river in blue. And what they've done in this planning map is dividing up the area into different zones. So you have Ohio City, downtown, Industrial Valley, Tremont. So this map is used to divide the entire area into different zones. Very useful in terms of planning purposes, and they were able to give a rough estimate as to what size, in terms of distances, what is a mile. By extension of photo maps typically would be single photographs upon which features are traced over. If I want to look at the entire block of photograph, I would create a mosaic, and this is the second one from our table content. in this lecture we're going to talk about, which is mosaics. The notion of getting a much larger picture of a region, of trying to get a bigger picture by using the photograph, not a topographic map, because we don't have the finances. In some instances, there are no finances to prepare the topographic map. So what they are left with is making use of the aerial photograph to create mosaics. And how the mosaics are done, there are two types. There are the controlled mosaic and the uncontrolled mosaic. Let's start with the easy one first. The uncontrolled mosaic is like a jigsaw puzzle. You would try and fix, cut and lay out parts of the photographs, each individual photograph, to get the best fit. So one photograph and its neighboring photograph, you try to get the best fit by cutting out certain areas that are duplicated, and by orienting it in different direction, you try to get the best fit, where the road will line up, where the buildings will line up, things like that. This is an example of a mosaic. You have a number of photographs, but what stands out of this photograph is, first of all, it's a larger area, and this larger area consists of a number of photographs. And what they try to do is try to get, if they're interested in mapping or finding out or mapping or showing the road network, the roads are shown very accurately. When you go into more detailed areas, these features may not directly match up, for the main reason that the aerial photographer said in earlier lecture, there are errors associated with them. So in this mosaic, the intent here is to show the delineation of the roads accurately as much as possible. Here is another set of aerial photograph. It's a series of color photographs, and the roads are depicted accurately. Now, it's very likely that this is a controlled mosaic where, for example, there is a coordinate system, and also the pixels of neighboring photographs matches up, within a certain specification, that the buildings in one photograph matches up with the same building in the other photograph. So very useful way of collecting data. The aircraft is flown in such a way that the aerial photograph takes usually between 50% overlap, or sometimes 60% overlap. And it is those overlap areas we would create our mosaics from. And also that overlap areas we would use to create our stereo models. So you'll take out the aircraft will be flown in one direction, and then a number of photographs taken out, and then turn around and come back. Another flight line or run is collected in terms of the aerial photographs taken out, and between parallel lines or between runs, there's usually between 30 to 40% side lap. And using these overlapping and side lapping areas, we are able to create our three-dimensional or stereo effect. Yeah, and on this slide, I need to mention that since we'll be working with mosaics, and mosaics, as I said before, typically used by planners, the accuracy is not as, it's not survey grade accuracy. Because typically planners would like to use mosaics, preferably a controlled mosaic, where there's a coordinate system defined. From that mosaic, they would be able to define an area of interest, which most texts refer to as an AOI, area of interest. Now, once they define their area of interest, that area, for planners' perspective, would actually cover a number of aerial photographs mosaic together. So mosaics, I need to identify here, is does not satisfy map accuracy standards because of the errors we spoke about earlier on in earlier lectures, errors due to relief and the camera tilt. On this slide, you see an example of another example of a mosaic, and from this example, an area of interest, an AOI, is extracted. So if you look here, it's two photograph, aerial photograph that was mosaic together, and they are properly georeferenced, so it has a coordinate system. From which we can extract, let's say we have a predefined study area defined by these three grids, 1, 2, 3. We want to, this is our area of interest, we want to extract that, and this is the result. Or we can have an alternative approach where, okay, our area of interest is the entire two photographs, and this is union, merging them together. Note well here that the computer tend to look for similar patterns, and if you look at this ridge, this road here is actually consistent across the both photograph in this union of the two aerial photograph that created a mosaic. Now let's say we have we are wanting a mosaic of this area here where it's not a regular shape but a polygon that incorporates areas from the one photograph and areas from the other photograph. We can get an area of interest like this, as shown here. Very useful in terms of reducing the amount of memory required to store the entire two images or the entire mosaic. There are traditional methods of creating mosaics. Mosaics were created traditionally by using pair of scissors and piece of paper and masking tape. They are assembled together by taking care that the details that are common in neighboring photographs are matched up to the best of their ability. Well-constructed mosaics have a general appearance of a single photograph. I would say the ideal mosaic where there seem to be seamless, where there has been a very good transition between photographs and a neighboring photograph, is one created using computer program. So mosaics generated by computer programs are very good to use, and it's much better than the manual or the traditional method of creating a mosaic. But how it was done long ago, using a pair of scissors, we have one photograph and we have another photograph. And this is my area of interest. What they would have done before was that they would have a cut line cut into the emulsion, into the actual diapositive, which is away from that common boundary. Okay, and using this cut line, the entire this area is discarded, and this is brought closer or try to match up to the best of ability to this boundary here in the neighboring photograph. And the same is done for other edges. So we're going to have another photograph on the above here that will match up with this boundary here, and we have another photograph here that will match up with this boundary. And usually that the cut line from the join line is usually would have been about 3 millimeters outside the join line. As I said in previous slides, there are two types of mosaics, and I wanted to identify some of the characteristics of the two types of mosaics. Now, the first type is uncontrolled mosaic. It's constructed from prints, or those what we call contact prints, hard copies of aerial photographs that are matched together with the details that they show with adjacent photographs. And your uncontrolled, it's called uncontrolled because no ground control or no X, Y, and Z coordinates are used in orienting the photographs to match up. Individual photographs are tried in the best way possible to match them up to the neighboring photographs. But because the photographs were taken as a central projection, and at the time the photographs were taken, there would have been some inaccuracies in terms of the tilt of the photograph. You know, the aircraft would not have been flying 100% horizontal or parallel to the terrain. Those errors would cause the mosaic to be not as accurate as you would expect it to be. But we try to reduce the errors by choosing the areas inside of the central areas of the photograph to be matched up to the central areas of the neighboring photographs. There would be some gaps. Double images, would persist in certain areas, but we try to get the best fit because remember, these are we are actually trying to match photographs with redundant information, and there might be some positional errors. A few millimeters are likely. And when we bring all of these photographs together to form the uncontrolled mosaics, it's a good map, it's a good picture for surveyors to use to do reconnaissance, or even foresters to use that when they want to define up the area in terms of stands. So it's very useful. An uncontrolled mosaic is made up by simply matching the like images. So what they'll use is to say the images that are similar in one photograph and look for the similar images in the neighboring photograph and try to match them up accordingly. This is an example of uncontrolled mosaic. And as you can see, there's a big gap here that we spoke about, one of the characteristics of them. That's because, the area, when they were cutting it out, they had to discard certain parts of those photographs. And because of that cumulative effect, you have an area that was not actually collected. Here you see another gap. 3 photographs were taken out in this area because of it being mountainous. But overall, if you look at it, the general essence of the area, there's a big ridge here, probably a snow-capped mountain, and you have a clear area in between, and then you have hilly areas again. So the general context of the area is actually captured, and this can still be used in various applications. The other type of mosaic is called the controlled mosaic. This is more popular and it has a lot more use to it than your uncontrolled mosaic. Why? Because in your controlled mosaic, you would typically use ortho-rectified photograph, which we spoke about in a previous lecture. The ortho-rectified photograph would have the effects of tilt and relief. The errors associated with tilt and relief be removed from each individual photograph, and also a projection system and ground coordinates will be used to convert each pixel. Each pixel in the mosaic will have a X and Y value, not a Z value. Control points are used and are plotted on a sheet of paper, and by fitting where the control points are by using a pen and putting the pen through the featured on the photograph that there is a ground control, and matching up that point with the grid that you would have drawn on a piece of paper that has that same control point. All right, then oriented other points. You would try your very best to fit the other images on the photograph the best of your ability. So using control points and a manual method, you would be actually introducing some ground control. Okay, the accuracy of controlled mosaics is better than that of uncontrolled mosaics, but it is still unsatisfactory. Now, if we do create a mosaic from using ortho-rectified photograph, that's an ideal scenario where we can use that in the computer model. In computer models, would generate a very good ortho-rectified mosaic of all of the photograph, which can be useful as a background in a GIS, for example, where we could trace out features, trace out layers of information based upon what is displayed on the ortho-rectified mosaic. A control mosaic displays the photographs that are very close to uniform scale. So at the scale at which the photograph was taken out, um, it will be the scale at which the mosaic will be. All right. Now, as opposed to your ortho-rectified, you can reduce the tilt and relief displacement, which is going to be a better product. The accuracy of a control mosaic approaches that of a good planimetric map. So a control mosaic can be used as a layer, or a layer where you can overlay it onto another data set of the same area. All right, so it's a good reference to bring some reality, some real pictures into that can be draped onto your surface in the studied area that you're working in. Now, I mentioned earlier on orthophoto. Orthophoto is a common product that is used in GIS as a background where we can uh, do on-screen digitizing. Orthophoto remove the effect of tilt and relief from vertical photograph, and once those errors of tilt and relief are removed, then we can start tracing out features that would be displayed on the orthophoto. The x and y coordinates will be accurate, but because we remove the effect of relief on the individual photographs to create the orthophoto, there is no Z value in orthophoto. But it is common that that orthophotos are used in many applications. Now, if you ever get an image of a study area, always, by all means, if you have a choice between orthophotos and mosaics, always choose the orthophotos. So the big question is, why do we ortho-rectify? Um, Rectification is important because in order for us to do things like GIS, if I have a data layer, for example, this is the drainage network, and I have a digital elevation model, and I overlay the drainage network over the drainage model, and I want to be able to present some realistic representation of the terrain. I would like to take some sort of an imagery, preferably some aerial photograph, and overlay that also onto the imagery, onto the DEM and the drainage network, in order to create this layer this layer such that it can be overlaid. We have to be using ortho-rectified photograph. Original photograph, as I said in previous slides, generated from the central projection, where the perspective center of the lens collects all of the light rays and enters into the camera. That center of the lens is the central projection upon which the aerial photograph was created. We have to convert that central projection to an ortho projection, and that's what we do in ortho rectifying a photograph. Here you see an example of using ortho photos to create a mosaic, a controlled mosaic, and it's very seamless. Another reason for using ortho photos, if you look at this example here, this is an aerial photograph of a road and its overpass. Now, if you look at the bottom road that goes underneath the overpass, the bottom part, as it goes below the overpass, it seems to curve upwards, and as it's coming out from the overpass, it's actually curving downwards. That is because of the effect of the terrain, and because the overpass is at a higher elevation than the underpass. The aerial photograph here is in error. Now, let's say if we take the aerial photograph as is here and we digitize along this road, both sides of the road, we will actually start introducing errors from about this location. The X and Y location will be in error. Actually, it's going up, and the X and Y location will be different. And you coming off here, X and Y is incorrect, and then it's correct here. So this area here that goes underneath the overpass will be digitized incorrectly. When you ortho rectify this image, this is the result, figure B. If you look at the road underneath the overpass, it's actually a straight line, which is what exists in the real world. Both sides of the road, straight lines. So this is a problem here that is solved in the ortho rectified photographs. This slide gives an idea of the effect of scale variation across a photograph. As you can see here, there are two houses, one on the top of the mountain and the other at the base of the mountain. Now, this house is in real world scenario, it's an identical house. So identical house, a split level house with various bedrooms and bathrooms, etc. Same size here at the base of the mountain, same size at the top of the mountain. Now, how does this show up on your aerial photograph? Well, the house that is on top of the mountain has a measured width of 2 centimeters. In actual real life measurements, it's 8 meters wide. On the photograph on top of the mountain, it's 2 centimeters, which is indicative of the scale being 1 to 400. At the base of the mountain, on the photograph, it's recorded as 6 centimeters. So actually at the top of the mountain, the house appears smaller than at the base of the mountain. At the base of the mountain, the scale is 1 to 133. So on your aerial photograph, if we were to take out a picture of this in this area as a vertical photograph, this house at the top of the mountain will be smaller than the house at the base of the mountain. So scale varies across your photograph. How do we auto rectify? One of the common software, commercial software, it's commercial but also relatively cheap, is using Erdas Imagine software. They do have a functionality where you can create ortho rectify photograph. Previously they used to call it Erdas Imagine Ortho Base, but now Erdas Imagine it does the auto rectification without any problems. You can actually create an auto rectify photograph with or without ground control, and it goes through a set of workflows that you might want to check out online, and you basically would auto rectify the single images. Multiple overlapping images, we would create we would use AirDAS Imagine, but not author-based. They have a new software called LPS. You might also want to look into that. Another non-software method is called differential rectification. And our next slide will go into details into differential rectification. Differential rectification, the terrain itself on the aerial photograph, or the actual photograph, is actually divided up into smaller sections, which is together with a digital terrain model and the camera calibration report, each pixel is rectified as if the pixel was on a flat terrain. It is necessary to know the elevation to the terrain, hence the reason why we need a digital terrain or digital elevation model. Elevations are obtained. If I have a stereo plotter, I create a stereo model. I will get the elevations from your stereo model in order to do the differential rectification. Here on this diagram, you see another method where they would use what we call an orthophotoscope, whereby your 3D stereo model is displayed, and you look through your eyepiece. So you have your stereo model, and you're able to see the 3D model. You have an aerial photograph, one photograph, and its conjugate, your stereo pair. What it does is that a film is used in the orthophotoscope, so you can see 3D. You can see the 3D stereo model in the orthophotoscope, and each pixel would be captured once. So you have here a film that actually goes across in this direction and captures each picture element, takes a snapshot, and the film is at the bottom here. That is transferred onto the film at the bottom, and then when it does this entire run, it goes around and it comes in this direction and does the same thing. Each slit is exposed and projected as if it's on a flat terrain. This negative, the orthophoto negative, is exposed through this slit, and from this negative it is developed, and you get your ortho rectified photograph of the 3D stereo model. Analog orthophotos are prepared using an instrument called orthophotoscopes, which is what we showed you a while ago. Follow the same procedure in the preparation of the maps. Instead of plotting, select the features in the base map. All of the points in the stereo model are actually photographed onto an orthophoto negative. So it's as if you are doing a capture of your terrain or your 3D model onto a new film, which is called your orthophoto negative, from which you would develop and you get your ortho rectified photograph. This is an example of a topographic ortho map. All of the features here is as if it's on a flat surface. The effect of height is not actually displayed, other than what you see here in terms of the contour lines were actually captured and placed as if they are on a flat surface. Orthophoto, the tilt and relief displacement can also be corrected by computational means using computers. This is more commonly used, and the orthophoto makes use of the software together with least squares adjustment to make sure that you get the best solution for the data that you input into the computer. Photograph is resolved into tiny aerial units called pixels. Each pixel has a grade level. Pixels are stored row-wise, and each pixels are analyzed individually and rectified. The camera tilts and elevations are known, so those things are predetermined, and together with your digital elevation model, you will need to have a camera calibration report where you will get all the information of where the fiducial marks are in the calibration report. You have to put that into the program, and then also ground control is important. The good thing about with the computer model is that there's additional benefits by actually using the software. You have a lot of enhancement. You can contrast and change and improve the color. You can eliminate some discontinuities between photograph if there are overlaps between photograph that does not seem to be consistent. You can smooth out that effect, minimize the effect of shadow, and then on top of that, you can also add other cartographic characteristics. Like, for example, if you have AutoCAD drawings, you want to include that into the system, you can easily do that because your orthophoto is a layer of information that you can have in other applications. This slide gives you some advantages of orthophotograph, and it's self-explanatory. Quite a bit of them I've already referred you to in my discussion, in my presentation. Orthophotos, being images, can use a wider spectrum of electromagnetic spectrum for specialized purpose. So you can have orthophotos of not just visible portion of the spectrum, but you could also have orthophotos for infrared portions and ultraviolet portions. Orthophoto is an excellent medium from which mapping can be done in inaccessible areas. So a very useful point here in terms of orthophotographs being used for areas that can be accessed if you by foot. Very useful. Excellent base or control layer for GIS. As I said before, you can have this as a separate layer in your GIS, and you can actually use that as a background for capturing more detail. The disadvantage from orthophotograph is not as much when you compare the amount of advantages. But anyway, the data sets are an image that needs interpreted by the user. So if you're not familiar with the data being displayed, it's difficult to interpret the information. There are also hidden areas where no data exists. So if you use aerial photograph that has shadows, there's a big disadvantage in orthophotos. Data shown on the image only represent that data above the ground, and even this may be sometimes hidden. With my orthophoto, I cannot do much, or I cannot do any spatial analysis. I can have it only as a background where I can extract more information or use it as a background to digitize other features from it. The last product of your photogrammetry, last significant product, is my DEM, digital elevation model, and this is the model that we would drape over other feature classes or other layers of information onto, to create my realistic representation of the real world. The heights of a DEM are obtained from my stereo model, and these points can be as dense as the observer see it. So if the observer wants to take spot heights that are within the model every 1 foot, he can do that, get X, Y, and Z values for every 1 foot in a dense network of that is defined by a 1 foot by 1 foot grid. Digital elevation model can be compiled with the help of analytical stereo plotters. So the present day stereo plotters can generate digital elevation models, which are very useful. Various patterns can be applied for data collection. We can use digital elevation models to extract contour lines. We can extract regular grid. You can do profiles, cross sections. Some books refer to profiles as cross section. We can tell the system to select random points. The number of applications using DEM is unlimited. It's an example of a DEM. Notice here the details of every aspect of the terrain is shown. There's a pond area here. And there is also some gutters in between here. Flat, smooth, relatively smooth areas. So the good thing about a DEM is that your DEM is as good as the data used to create it. So if you're gonna if you want a DEM that's gonna pick up every detail, then you need to make sure that those details are the heights and the X and Y location of them are included in the creation of the DEM. DEM may be used for various purposes: for hill shading, contouring, volume computations, creating 3D models, doing what if scenarios. What if I put a telephone tower at a point location A? Where can I put another telephone tower that are indivisible? And the list goes on and on. There's a lot of applications using DEM for drainage analysis. Delineate for me what is the drainage basin for a given area. Most DEM is stored either in the form of a regular grid, or some of them are actually stored as an indirect or derived dataset called a triangular irregular network called TIN. Very common surface. Okay, this concludes our discussion about photogrammetry and its products. As I said before, there are many products, but in this lecture I identify some of the common, more popular products. Please go ahead, download the information, download the PowerPoint with its notes, review the material, and we will continue with our lecture series.